Assalamu alaikum. This is the subject of Geotechnical Engineering 1. The course code is CE221 and this is the second week's lecture. So this is the second week lecture after the corona pandemic. So first we will recite this dua, that is Rabbi Shrah li Sadri, that means my Lord expand my chest. So being a student, we all should be remembering this dua and we should be reciting it day and night, okay? So that will help us learn easily and inshallah Allah helps us in learning. So starting with our today's topic, previously we started with the Terzaghis lecture, the consolidation theory, that what is consolidation, and we learned some basic. Today we will further go with in detail of consolidation. So today's topic is Terzaghis one-dimensional consolidation theory. So how does that help us? It helps us in estimating the magnitude, that means the amount of settlement. For instance, if we have a clay layer that is underground at some distance from this ground surface, and the magnitude would tell us that how much amount of settlement would happen. So if I draw a ground surface here, and let's say this above all is sand, and here we have this clay layer that is having the thickness of maybe 2 meters. So this is clay here, and let's say this is sand. So once we construct a big building here, a big warehouse, so due to the load that is coming from that warehouse on top of the clay, so Terzaghis consolidation theory estimates that how much settlement would happen. And by settlement I mean, if this is the 2 meters the initial thickness, then after settlement, due to the load that is coming from the ground surface, how much reduction would happen. So maybe this new reduced is, let's say, 1.8 meters, new reduced depth. So now as the clay layer is settling, so does the ground would settle. That means the ground would also move down by an estimate of 0.2 meters. So this estimation that if the clay layer is 2 meter thick and if the load is coming this much kPas, so by using Terzaghis one-dimensional consolidation theory, we could tell that in a 2 meter thick clay layer under a certain amount of load, how much settlement is going to happen. That in the example we just did on this board here, 0.2 meter. So this is estimated by Terzaghis one-dimensional consolidation theory. So this is the first advantage. The second thing is rate of settlement. So we know now that this clay layer is going to settle an amount of 0.2 meters. So we also want to know that is it going to happen immediately or is it going to take a longer while. So we have already discussed in our previous class that clay, because of its low permeability, takes a much longer time depending on the permeability of the clay layer. So by using Terzaghis theory, we can tell that okay, if this is the load and this is the amount of settlement that is going to happen, so we can tell that okay, this much settlement is going to happen in 7 months, maybe, or 25 years, or maybe 10 years. So all this could be estimated by the Terzaghis one-dimensional consolidation theory. One more thing regarding this is that why is it called a one-dimensional consolidation theory? Because in this, the main assumption that is actually very far from real is that water movement only occurs in one direction. So if this is the clay layer, so according to it, because we know from our last lecture that in consolidation, water moves out of the voids of the soil, and due to the rearrangement of the particles, the volume of the soil reduces. So in this, according to Terzaghis one-dimensional consolidation theory, water can only move in upward direction and only in downward direction. It does not move sideways. This movement does not happen, and this movement of water does not happen. Water only moves up and down, and obviously you can see that it's a two-dimensional figure. So it's a two-phase problem, okay, that is considered by Terzaghis. So we'll see in details when we'll do the numericals based on the one-dimensional consolidation theory. So moving forward, so let's see what are the assumptions. All right, so assumptions, first one is that soil is saturated. So if you remember from our last lecture, we discussed that we are only considering for our geotech course a soil saturated soil, because and by saturated soil we mean that there is only water in the voids of the soil and there's no air, and the voids are completely filled with water, so that it defines as a saturated soil. So this is also the first assumption of Terzaghis consolidation theory. Second assumption is that water and soil solids are incompressible. So that means there would be no reduction in volume of soil due to the compression of the soil particles. By that I mean breaking or fracturing of the soil particles or compression of the water. So we are totally neglecting. In reality, there might be some compression occurring in real life, but for our Terzaghi's theory, Terzaghi's thought that there would be no compression in water and soil solids. So that means the only reduction in volume would be brought about by the movement of water out of the soil voids, and we have already seen that it's going to be only in one direction, that is horizontal direction. Third assumption is that linear relationship between pressure and volume change. So by that I mean that if we perform test on the soil, we apply a load and we see the relevant volume change in the soil, so it is going to be a linear relationship. So to explain this, if I draw a graph here, so if this is the load or stress that we are applying on the building and this is the deformation, so it should be approximately linear. All right, maybe in this direction, it can be here or here, but it's almost like a straight line. So this is what is meant by linear relationship between pressure and volume change. So if the pressure is increasing, so is the deformation increasing. And we have already seen assumption number 4, that the seepage flow is in one direction. Darcy's law is applicable, and by Darcy's laws it means that V is equal to Ki. V is the velocity of water, and K is the permeability of the soil, and I is the hydraulic gradient. So if we know that already, that I is equal to H over L, where H is the head causing flow and L is the length of the seepage path or the water flow path. So but for now we don't have to worry about it. We will discuss that in detail in our next week's lecture. Sixth assumption is that deformation is one dimensional. So we have already seen from the figure that deformation is only going to happen in one direction. Okay, just to jog your memory, so this is the clay layer, so deformation is only going to happen in this vertical direction. All right. Assumption 7, soil mass is homogeneous, which actually is very far from real. And the 8th assumption is that coefficient of permeability is constant. So in real life, if this is the ground surface and this is the huge depth of soil, so definitely on the top permeability will be different, here it will be different, here it will be different. But for our purposes, or for the Terzaghi's theory, we assume that this whole clay layer would have one uniform value of permeability. So these were the assumptions, okay, that were made to put forward the Terzaghi's consolidation theory. Now what is the problem is that large differences in nature and theory occur in real life because large volume of air in the voids of the soils are present in real life. So the basic assumption that soil is saturated. So in real life we don't have saturated soil, we also have a third phase, that is the air in the voids of the soil. So that's why we have the differences in the predicted settlement and real life settlement, but still it is used in field even nowadays, and for many years it's happening. Now we talk about consolidation characteristics. So first one is Cc, that is compression index, and then we have Cv, that is the coefficient of consolidation. So Cc, compression index, in bracket I have written amount, so that means it will tell us the amount of settlement that is going to happen in the soil specimen. So the same thing we have discussed already, that we want to know that the Terzaghi's theory would tell us the amount of settlement, or in inches or millimeter, that how much deformation is going to happen in the soil sample. And secondly, coefficient of consolidation will tell us the time that in how many years the clay would settle how much in depth. So now we talk about one-dimensional consolidation test. So I have drawn a diagram here. Let me zoom that up for you. Just a minute. All right. So this is a typical apparatus of a one-dimensional consolidation apparatus. We already have that in our lab, and you might have performed that in your lab portion. So this thing here, this whole orange mass, this is the soil sample that we have placed, and this boundary here, you see, this is the portion here. This is the consolidation ring. All right. So let me write that for you. So this purple thingy is the consolidation ring. So this gray hashed portion, these both of them are the porous stone on top and bottom, porous stones. And you see this multicolored small thin lines, these are actually filter papers. Oops. Filter paper. So this is a filter paper, and this whole thing apparatus is submerged in water. This is the loading frame or loading cap. So this is the load applied, and this is the deformation dial gauge, DDG, I'm indicating with it. So what we actually do is that we will take a soil sample, we will place it inside a ring, consolidation ring, and on top and bottom we'll place the filter papers, these one, and then on top of the filter papers and bottom of the filter paper we'll place the porous stone, and then on the whole assembly we'll place a loading platen. Alright, and on that loading platen we'll apply this load sigma. Alright, that is going to be a vertical load. Alright, so once we are applying load, what will happen? The excess water would move out from this filter paper into the porous stone. Alright, and as a result consolidation will happen, and that means there would be some volume change, and we have already seen that volume change is going to happen only in one direction. So that means this, after some time, this height of the soil specimen would reduce. Alright, because this whole thing would be compressed down due to the load applied. And from the deformation dial gauge you will see that once we have applied load, so with time how much deformation is happening. So to explain this in a more clearer way, I have drawn this. I don't know, just a minute, I don't know why it is stuck. Okay, all right. Oh, here it is. All right, so we were talking about the consolidation ring. So if I look at the plan view of this ring here, so it's circular, having almost a diameter of maybe 2 to 3 centimeters. All right, so we will place the soil specimen inside it. Okay, so if I draw the further cross section, so the edges are little bit trimmed at the end like this. So these are the edges, they are trimmed. So if this is the soil specimen, so we will punch it inside it, and once we will punch it inside it, what will happen? This soil will come inside it, we will trim off any extra on the edges, and then we will place this, this is the ring, so we will place this here in the apparatus. All right, so all right, so this was the basic about the consolidation test. Furthermore, there are two types of consolidation test. First one is called the floating ring. All right, so the floating ring apparatus is just like the one I have drawn. All right, so it's a place, the soil specimen is pressed inside the consolidation ring, and the porous stone and the top and bottom, and then we have loading plate, and this whole thing is placed inside a container. So there is nothing else. So this is called as a floating ring. The second type here is called as the fixed ring. So in the fixed ring apparatus, what happens that we have this soil specimen here. All right, so the ring here, you see here, it's a different ring. You see here, this is the consolidation ring, so it has an outer bench here, right? This is the outer bench. Similarly here we have this excess bench here. So what will that do? That will fix it inside the apparatus. In the previous sample or the previous apparatus, you saw that the ring was free, and that's why it was called as floating ring, and this ring is fixed inside the apparatus. All right, so that's why it's called as fixed ring. Similarly, we have porous stone on the top and at the bottom. The one additional feature is that you see there is an outlet valve that is coming from here, all right, on both sides. So the additional feature of this test is that we can also find out permeability, that is the K value, out of the test. So because we know that we have some soil specimen and we have water in that, so and we are applying load and we are also noting the time, that how much load is taking how much time. So we can also predict the permeability by noting the amount of water that is coming out of these drainage valves. So these were the two types of the consolidation apparatuses, first one being the floating ring and the second one is the fixed ring. So this is also called as an odometer, all right, and generally some people call them directly as cone tests. So you should know that when they say cone test, so they mean consolidation test. So so what we are going to do is that we require undisturbed or maybe a remolded specimen, and that is trimmed inside the consolidation ring. I just told you how that is going to happen. So this is a picture of the undisturbed sample that we achieve from the field, that we take this whole box, and this is approximately maybe 1.5 feet and this is also maybe 1 feet. So these are almost the dimensions, 1 feet by 1 feet. So this is the big box. So out of this box we can take a number of samples to be tested for the consolidation test. And then we require so this is the first thing. Second thing is we require porous stones are placed on top and bottom of the soil specimen. And why do we need that? Because to allow vertical drainage of the water. Thirdly, we require vertical load is applied on the soil specimen, and then dial gauge is used to measure deformation. Then point 5 is soil sample is fully submerged in water, fully saturated. Clay has, and why we do that? Because clay has lowest strength and greatest compressibility, or we call that as the worst case scenario. This is the worst case scenario that can happen for a clay. So we want to check our soil in the worst case scenario, that how much load is going to take and how much settlement is going to happen and in how much time that settlement is going to happen. So generally the rule is for the consolidation ring specimen is that thickness is 1/2 or 1/3 of the diameter. All right. So once we have set up the apparatus, I'll draw a small assembly again here, that we have this apparatus and we have porous stone in top and bottom. Then this is submerged. This is a fixed ring example. So we apply load. Now how do you apply load? Firstly we have zero load and then we have 0.25 tons per square foot. Now I apply 0.25 TSF load in the specimen, and as soon as I apply load in the specimen I will turn on the stopwatch and I will note its reading. All right. So so what readings I'm going to take, because this 0.25 TSF is going to stay on the sample for 24 hours. All right. So as soon as you place the sample as soon as you place the load in the specimen, you turn on the stopwatch and you start to note the deformation dial gauge reading. So two readings basically you will be taking at different times. Okay, first thing is apply a particular load and then turn on the stopwatch, okay, and note the deformation dial gauge reading. So what are the times? So they are mentioned here. Generally the time of reading is after first reading comes after 0.25 minute. All right, that is at 20 seconds, and after 0.5 minute, that means after 30 seconds, 1, 2 minute, 4, 8, 15. So the process is I'll place the specimen, I'll place the first load increment, that is 0.25 TSF, and then I will start the stopwatch and note reading at these increments. And what readings I'm going to take? I'm going to note the reading of the deformation dial gauge. So at the end of the day, when I'm completing an experiment, so I will have the data that for a load of let's say 0.25 TSF, I will have time and dial gauge reading. So time value at 0.25, at 0.5, 1, 2 and so on would be this, and this way we are going to note the reading. But this is for a particular load. Now, so once you are done, generally this load has to stay for 24 hours, but we can if we want to stop the test before 24 hours, then what we do, we need to have a look at the deformation dial gauge reading. If the readings become constant for 3 to 4 values for a certain time, that means that the sample has deformed under this particular load. So once this readings are coming constant, then you can place the next load increment, that is 0.5 TSF. All right, then again, once you place the load, turn on the stopwatch, note the deformation dial gauge readings, and keep the process. And again, either wait for 24 hours or wait for the readings to become constant. So once the any of the two things happen, then you place the second load. So this is the loading procedure. So we keep on loading. So once we are at 16 TSF load, all right, and we have no